Today we will give a quick derivation of the Einstein field equations. Our starting point will be to look for a torsion-free metric theory of gravity which reduces to Newtonian theory in the weak field slow motion limit. We will be guided by mathematical simplicity and elegance. Let GAB be the metric, then gamma A, B, C we're going to write as the Christoffel symbols. Of the Levi-Citiva connection. Riemann tensor is given by dCABT minus dTABC is gamma ACE EBT minus gamma A DE gamma EBC, and RAB, the Ricci tensor, is RCACB, and that's equal to DC gamma CAB minus DB gamma CAC plus gamma CEC gamma EAB minus gamma CAE gamma EBC. The Ricci scalar is GAB RAB. We are going to define our theory through an action principle. We're going to have delta S equal to 0. S we're going to take to be the simplest thing we can think of, which involves the curvature. And that's going to write as R over 2 kappa. Kappa is just some constant, plus matter Lagrangian times dV, which is minus g d4x. We're going to vary this with respect to metric variations GAB. Okay, well, delta R is RAB delta GAB plus GAB delta RAB. So GAB delta RAB is equal, so I'm varying this thing here, GAB times DC delta that thing minus DB delta that thing plus order gamma terms. The difference between two connections is a tensor. So that thing there is a tensor, says that. I can evaluate this expression here in coordinates in which gamma is 0. So that term goes, and then this thing will be equal to the covariant derivative. But this is a tensorial relationship, and so is this. So this must hold normal frames, not just Riemann normal coordinates. So that's the gradient of C. That should say delta gamma CAB. Now I could swap indices around, so the contraction here would raise that to an A. So I want to call it C, so I'm going to call it GBC. Delta gamma B, these were contracted, so A, for instance. So that's DCAC for a vector AC. And therefore, delta the integral g AB, let's put it over here, delta R AB root minus g d4x is the integral of that dv. And the variation of that is 0 because that's a total divergence. So the next thing I need to do is I can drop that term in the equations and just left with this one. I now want to work out to see what happens when I vary the root minus g. Let A be a matrix with components A, I, J. Then A times the adjoint of A is the determinant of A times the unit matrix. So components A, I, J, adj A, J, K is det A times delta I, K. Let's evaluate it when I equals K. So therefore we get the sum over J AI J I is det I. There's no sum over I implied in this equation. Well, this shows that if I differentiate this determinant with respect to Aij, I just get the adjoint of A Ji. The point is that when you work out the determinant, you cross off the column and row associated with each AI and work out a subdeterminant. So this adjoint is a cofactor which doesn't depend on the Aij. So therefore this expresses the determinant as a linear combination of these objects here. Now that's equal to the determinant of A times the inverse. Let's apply this to the inverse metric. dg inverse by dg AB is equal to g inverse, that's shorthand for the determinant of course, times g AB. And that tells me that dg by dg AB is g the minus sign g AB, or d root minus g by dg AB is minus a half root minus g AB. So if we were to look at delta root minus gr, that gives me delta r root minus g plus r delta root minus g. And this thing we worked out a second ago, it was just that term there, well up to the addition of a total divergence RAB. And this thing gives me a minus a half RGAB. Let's just have lower indices, of course. It's supposed to be the inverse of the thing we were considering. Now we define TAB to be minus 2 over root minus g delta the matter Lagrangian by dg AB. Therefore delta S is 0 implies, so that was from there. We get RAB minus a half RGAB is equal to kappa TAB. And those are the Einstein equations if we can determine what kappa is. One thing we can do with this equation is this is the trace reverse of R. So I can also write it as RAB is kappa times the trace reverse of T. And that's going to be convenient. Let's take a metric ds squared minus c squared e to the 2 phi over c squared dt squared plus dx squared plus little o1. So little o1 just means it goes to 0 as c goes to infinity. Right, let's work out the geodesic equation. L, the Lagrangian, is going to be minus c squared e to the 2 phi over c squared t prime squared plus x prime squared plus little o1. So dl by dt prime is dl by dt, and that gives me c squared e to the 2 phi over c squared t prime prime is 0, which shows me that t prime is equal to gamma e to the minus 2 phi over c squared for some gamma. This is the special relativity gamma. But we can also write this out as t double prime plus 2 di phi over c squared xi primed t primed is 0. dl by dx primed is dl by dx, do for each component. That tells me that x double primed with component is equal to minus di phi e to the 2 phi over c squared times t primed squared plus little o1, and that's minus di phi t prime squared plus little o1. We can write this out as xi dot t prime dot times t prime so that cancels that, and therefore we get 1 over t prime xi dot t prime dot minus di phi plus little o1. From here that gives me e to the 2 phi over c squared times xi dot e to the minus 2 phi over c squared dot is minus di phi, gives me xi double dot is minus di phi plus little o1. The extra term we get here brings down 1 over c squared term, so that's why it's absent here. So we get x double dot is minus grad phi. So that's the acceleration due to a potential phi in Newtonian theory. Next we want to work out what phi is from the Einstein equations. From these equations that we have here, notice that gamma I t t, so we're comparing these equations with d2xa by d2 squared plus gamma A, B, C, dxb by dtor, dxc by dtor is 0, geodesic equation. So if we go back to this equation here, you can see that's di phi plus little o1. All the other Christoffel symbols are little o1. Next, we had this equation here. We're going to consider pressure-free dust. So the energy momentum tensor is rho UA UB, where UA is dxa by dtor, which for static configuration is T0. Now UA is minus c squared, so UT is minus c squared, and therefore UT squared is minus c squared GTT plus order 1. Just inverting that. The metric is essentially diagonal, so I get that. Therefore, TTT is rho c squared times another c squared into 1 plus order 1. Now, RTT is dc gamma c tt minus dt gamma t c c plus gamma c e c e t t minus gamma c t e gamma e c t. Recall the only non-trivial Christoffel symbol is gamma ITT. So the only non-trivial term here in the limit that c goes to infinity, well, that must be an I then. That'd have to be a t, but then we get gamma TTT, and that's trivial, so we don't get anything from there. That would have to be an I, but that gives an I down here, so that would go to 0. That would have to be a t, which means it would have to be 2 t there. That would be a t again, so that's nothing. So we get di gamma I tt plus little o1. Now, that's going to be equal to del squared phi plus little o1. And we know that's equal to kappa times t minus a half g t c c. Well, t c c is g t, and therefore t minus a half g t times tcc is equal to a half t into 1 plus little o1. Therefore, del squared phi is equal to kappa over 2 times rho c to the 4th into 1 plus order 1. Compare this with Poisson's equation. So L squared phi is 4 pi g rho. We have consistency provided we take kappa to be 8 pi g over c to the 4. And thus we have RAB minus a half RGAB is 8 pi g over c to the 4 TAB, which is Einstein's equation. In the limit we have weak field non-relativistic motion, we get consistency with Newton's theory of gravity.